Okay, so welcome everyone to another year of JIPS. And our first speaker is Vittoria Silvestri from University of Roma, La Sapienza. She'll speak about Hastings Levitov. Thank you, Vittoria.
Thank you, and thank you very much for the invitation. So today I would like to tell you about some recent results on a version of the Hastings Levitov growth models on the upper half plane. And I always like to start my talks with some word of motivation. Why should we consider this kind of models? We're interested in building mathematical models for the formation of fractal structures in nature, like the ones I depicted here. So we have branches of a tree, lightning in a thunderstorm, different types of corals. And you could think that these structures form by aggregation of particles. And to start simple, you could try to build a discrete mathematical model for the formation of these structures. So you choose an underlying graph. Here is the two-dimensional lattice in this picture. And you start with an initial seed, an initial aggregate, say one particle or a cluster of particles, and you want to aggregate more particles to it by attaching a new particle on the cluster boundary according to some probability measure. And the probability measure that you will choose on the cluster boundary will determine the kind of model you are considering. So in this class, for example, the Eden model on the left, in which we aggregate according to the uniform measure on the outer boundary of the current cluster. And this simulation is Eden model on Z2, and it's due to Jason Miller. Otherwise, we can aggregate according to the harmonic measure on the external boundary of the cluster, which means we take a simple random walk, start very far from the cluster boundary, let it run until it hits the outer boundary of the cluster and aggregate the next particle there. So that's diffusion limited aggregation. It's a famous model, and this simulation is due to Van Sambe-Farait's diffusion limited aggregation on the two-dimensional lattice. And you can interpolate between these two models by aggregating according to a fractional power of the harmonic measure on the cluster boundary. And these are called dielectric breakdown models. So you can see that these models are easy to define. You just prescribe the probability measure that you choose, that you use to choose the next aggregating location. But the large scale structure of these clusters seem to depend on the underlying graph. For example, in the Eden model, we can see that the cluster looks a bit more stretched in the preferential directions of the underlying graph, but this is very evident in diffusion limited aggregation. So around 2000, physicists and mathematicians started wondering, should we try to build aggregation models directly in the continuum? And Carlson and Makarov proposed to use conformal maps to build random aggregation directly on the complex plane. And roughly at the same time, Hastings and Levitov used these ideas to define a one-parameter family of models, which now go under the name of Hastings-Levitov models. And the good thing about this class of models is that they're amenable to simulations. Already in the original paper of Hastings and Levitov, there are several simulations. And because clusters are described via conformal maps, we have many tools from complex analysis that we can use to work with these clusters to analyze them mathematically. The bad thing about these models is that the use of the Riemann mapping theorem restricts us to the two-dimensional case. So everything I will discuss will be planar growth. And I won't tell you what the original Hastings-Levitov models are. I will go directly to a version of the Hastings-Levitov models that we considered. And then towards the end of the talk, I'll tell you the original definition of Hastings and Levitov. So to define the model, we want to start from, no particle at all, and we aggregate particles on the upper half plane according to, we would like to use harmonic measure from infinity. So we would like to mimic diffusion limited aggregation. In the discrete setting, you start a simple random walk from infinity, and now start a Brownian motion from infinity and aggregate according to its heating measure. So to start with, we can think that, well, the first aggregation point, without loss of generality, we can take to be the origin. And there we grow our first particle. So for us, a particle is just a slit, a vertical line segment. And the way we describe this particle is via a conformal map F. So we know by the Riemann mapping theorem that there is a unique map which maps the upper half plane to the upper half plane minus the slit, provided we ask that F maps infinity to infinity and we fix the behavior at infinity. So because this correspondence between particle and map is one-to-one, we will describe particles by describing via the unique map that grows them. So this is what I mean by attaching one particle at the origin, and now we would like to keep on attaching particles according to harmonic measure. And the way we define this model is we want the next particles to attach on the aggregate. So the next attaching location has to be, well, now the aggregate only consists of one particle, so the next particle has to attach on the slit and it cannot attach anywhere else on the real line. And now the idea of Carlson and Makarov comes in. If we want to determine the next attachment location, we might as well forget for a second that we had already grown one particle and map it out by applying F inverse, which takes the slit and it maps to this red interval. And now Brownian motion gets mapped to Brownian motion because it's conformally invariant. F maps infinity to infinity. And so if we want to determine the next attachment location on the slit, we might as well just choose a uniform location on the red segment and attach the next particle there. So when I say attach the next particle, I mean we are going to apply a conformal map F2 from the upper half plane to the upper half plane minus a slit. And F2 is just the original map F, which now I called F1 just to encode the fact that it grows the first particle, conjugated with a random translation which centers the slit at the new attachment point. And now we have to remember that we had already attached one particle, so we're going to grow it back by applying the map F1, which takes the red segment and it grows it into the original slit. But now F1 acts on this second particle and it deforms it. So it will look like, a bit curved in the X. And if you compose these things together, you realize that you've simply applied F1 composed F2 to the upper half plane. So we can keep on going. If we want to attach the next particle, we can for a second forget that we had already grown two particles and map them out via F1 composed F2 inverse. So the cluster will be mapped to this red interval. And there we choose a uniform point and attach the third particle there, again via a map F3, which is obtained by a deterministic map F, which grows the slit at 0, which is conjugated with a random translation, which centers it at the new attachment point. And now we have to remember that we had already attached two particles, so we grow them back by applying F1 composed F2. And what this does is it takes the third slit and it deforms it into this curved particle. So if you compose things together, you realize that you've just applied F1 composed F2 composed F3. And so this tells us how to build a cluster with n particles. We have to apply a conformal map phi n, which maps the upper half plane to the upper half plane minus the cluster. And this map is random. It's given by the composition of n random conformal maps. The way these conformal maps are random is via the attachment locations. So they're all obtained by a deterministic map F, which is the one that grows a slit at 0, conjugated with a random translation, which centers it at the attachment point. And the attachment points are obtained as follows. You take your cluster with k particles, map it out. It will go to an interval, a random interval of the real line. There choose a uniform point and that will be your next attachment point. Please feel free to stop me at any point if you have questions.
So can I ask a question? Maybe it's a simple one. So the harmonic measure of the trees of what you're growing goes to 1. So the conditioning becomes weaker and weaker. Is this correct? As the time progresses? So conditioning that you attach to something that is already grown becomes the same as just...
You could attach anywhere else on the real line. So this cluster will always be of a finite size.
So it's not on a disk, okay. Mm-hmm.
Yes. So in fact, I'll comment on this in a second. So the regime we're interested in is we want, of course, to send the number of particles to infinity, but we want to rescale things so that the cluster has finite size. And this corresponds to send the size of each single particle to 0. And the way you have to adjust things to get a cluster of finite size is, well, we control the size via the half-plane capacity of the cluster. And for the cluster to have half-plane capacity of order 1, we would like to attach slits of order 1 over square root of n, because the half-plane capacity scales like the square of the length of the slit. And so this tells us that the half-plane capacity will be of order 1 over n. We attach n particles, we have half-plane capacity of order 1. And we can introduce a parameter t, which modulates this half-plane capacity. It can grow from 0 to infinity. So this is called the small particle regime because the size of each particle is going to 0 and the number of particles is going to infinity. And we would like to study large-scale behavior of these clusters in this regime. Are there any questions about the model? Okay, so to get an idea of what these clusters should look like, we can try to simulate them. And I'll show you some simulations. What we did here is we didn't simulate the cluster itself, the boundary of the cluster itself, because the boundary is very badly behaved. And so computationally, it's much easier to simulate an envelope of the boundary of the cluster, which means you take a line here, which is bounded away from the real line, but very close, say imaginary part of z equals epsilon, for epsilon very small, and you plot the image of this line under the map phi n. That will be a nicer curve, and we can simulate that. So here are some simulations. This is a constrained Hastings Levitov cluster on the upper half plane with 500 particles. And you can see that, well, you can see particles which are, so all particles are on the boundary, but here you can see some particles in the envelope. And you should think that there is a tree structure which is hidden in here, which is not plotted in this picture. And you can increase the number of particles to 1,000, 5,000, 10,000 particles. And you can see that these clusters look elongated. And we can also keep track of the attachment points in the interval, which corresponds to the cluster growth. So remember, you have your cluster. If you map it out, it will get mapped to this to a red interval, to this red interval. It's a subinterval of the real line. And that's the interval where you choose your next attachment point. And what we did in the second picture is we kept track of the movement of the extrema of this interval, the left and right extrema, the left and right extrema get pushed away from the origin as the cluster grows, and you can plot exactly how they move. So that's the left extremum, and above is the right extremum. And inside, we plotted the attachment points, which, as you can see, live on the interval. So one could wonder, is there a scaling limit? How elongated are these clusters, actually? And so here is the result that we proved with Nathaniel Berestiki in Vienna. So first of all, let's see how the interval grows. remember, L and R are the extrema of this random interval. What we can show is that well, these extrema move predictably. So they are concentrated around the half square root of t log n. So ignore this epsilon and capital T, there shouldn't be there. So these extrema move predictably exactly in the same way. R and T is close to square root of t log n divided by 2, and same thing for L and T, which is the left extremum. And in particular, the length of the interval grows in a predictable way. L and T is concentrated around square root of t log n as n goes to infinity, which says that this red interval, which is obtained by mapping out the cluster with NT particles, has a diameter of, as a length of the order of square root of log n. What can we deduce from this on the geometry of the actual cluster? Well, the fact that the actual cluster has height bounded by a constant which depends on t is in fact a deterministic statement, which just comes from the fact that the half-plane capacity is bounded. But from the above result, we can deduce that the diameter of the cluster explodes as n goes to infinity. So the clusters are indeed very elongated, and their diameter is of the order square root of log n, where there is a constant which depends on t. We can prove that the ratio goes to 1 as n goes to infinity. So this is what we call explosive behavior. We have clusters which have diverging diameter as n goes to infinity, although we scale things so that they have finite half-plane capacity. And let me also comment on the fact that I described the behavior of the length of the interval, of the random interval corresponding to mapping out the cluster at given t. T is a parameter here, but in fact we can get a uniform control in compact sets for t. So we also have this kind of results. And we proved that the height is bounded by a constant which depends on time, but we don't believe that to be tight. We believe that the real height should be something like 1 over square root log n, so that the area of the cluster stays of order 1. There is a question. I see someone raise their hand.
Oh yeah, hi. I was wondering if there's a typo in your main theorem. Would you mind to go one slide back?
Sorry, can you say it again?
Back? Would you mind? I was wondering if you have a typo in your main theorem. Yeah, I noticed the right edge R and T and the L and T, they kind of have like a similar growth. Not like one is going to the right, the other is going to the left. Am I right? Or maybe one of the minus sign should be the plus sign. Yeah.
Oh, R and L, you mean? So here the left extremum is minus L.
Ah, okay, fine.
So L is just the distance from the origin. Okay, so I was saying we expect the area, that the height should be of order 1 over square root of log n, so that the area of the cluster stays of order 1. And also we expect our result not to depend on the choice of the particle shape. So everything we've done is for a slit particle, so a vertical line segment. But in fact, if you take localized particles like little spheres or maybe half disks, we expect to see the same kind of behavior. The behavior should not depend on this choice.
Excuse me, there's another aspect to these shapes, the envelope of the cluster that you haven't mentioned. There's a sort of wiggling behavior on top. And so you have a zone under the cluster, which is empty. The zone where it's wiggling is getting thinner and thinner, it looks like, from the simulations. I'm not sure I'm making sense, but there's a you can see there's a sort of a thin layer where it's going up and down and up and down. It isn't getting close to the real line across most of the cluster. And you could ask for the thickness of that bit where it's going up and down. Do you have results on that?
So you mean, depending on the choice of this epsilon, you would like to know how the thickness of this part of the cluster scales? I'm not sure I understand.
I think what it means is that, so in this simulation you only see, so I guess what you took is you took the final function after n and took the line and saw where it goes. So yeah, the only thing you see in the simulation are all of the less particles, but the particle size goes to 0. So the width that it sees goes to 0 is just I guess just the particle size goes to 0, and it's not a real phenomena. It's just a way that the simulation is drawn. I think this is the answer to this question.
Yes, so we just plot this blue curve, and of course, the smaller you take epsilon, the more you will see the shape of the actual cluster. The larger you take epsilon, the less you see the structure. And ideally, you would like, if you take epsilon to be like, well, of the order of the length of each particle, then you will at least see the last few particles.
Okay.
Okay, so this is the result, and I'd like to give you a sketch of proof. I just want to explain where the square root of t log n comes from, because this is a very simple argument. So we would like to control the length of this red interval, which is obtained by mapping out the cluster, and we would like to understand how fast it grows in n. So to understand how fast it grows, you could think of attaching a few more particles, and you could ask yourself, how do the extrema of the interval move? So here we had a cluster with k particles, which corresponded to this red interval. We attached m further particles, which get mapped to these blue segments here, blue intervals. And now both R and L will get a push far away from the origin, and we would like to quantify the push. So rather than fixing the number of particles and asking ourselves, how do the extrema move, we could go the other way around, and we could say, let's assume that at some point the length of the red interval is some given number L. How many particles do we have to add for the interval to grow by a proportion of its length, by delta L? And to understand this question, we have, well, first let's look at how the extrema of the interval move under one particle arrival. And let's focus on the right extremum of the interval, and then the same arguments will be used on the left. So we have our cluster with k particles. It gets mapped out to this red interval, and we choose one attachment point uniformly at random, attach the blue particle there, and then grow back the first k particles, which will give us the blue particle on the actual cluster. And to see how the right extremum is moved by the arrival of this new particle, well, we just map out the slit by applying the inverse of the map that grows it. And we see the image of this extremum under this mapping out function. And that will give us the new interval. But this mapping out function, well, it's obtained from an explicit function just by conjugating with a random translation. And so we can estimate how much applying this function moves points. And the key observation here is that the movement, the push that the right extremum gets by the arrival of a new particle only depends on how far from it the new particle lands. And so this suggests to split the red interval into several regions according to how far they are, how far the particles are from the right extremum. So we introduce these sub-intervals ij, and the length of ij doubles as you move away from the right extremum. And let's estimate the push that the right extremum gets when a new particle lands in one of these intervals ij. Well, this push is approximately some constant divided by n times 2 to the j, which is the distance, roughly the distance at which the particles are from the right extremum. And when I say approximately, I mean we have good upper and lower bounds with small errors. And according to whether you use upper or lower bounds, you can use this to build super martingales or sub-martingales. So if we split, we want to look at m arrivals. We want to look at the movement of the right extremum after m arrivals. And so we can split the push that R gets by the arrival of m particles into the contribution of the push that it gets by particles, from particles that land in each interval ij, from a minimum scale to a maximum scale. The minimum scale here will be the size of one slit, and the maximum scale will be of the order of the entire interval. And so if we look at the contribution to the push of to the right extremum given by particles landing in ij, well, that will be the sum of the push of each particle, where we take it only if it lands in ij. And this is easily estimated when you have a control on the length of the entire interval, because this push we have already estimated. The probability that the particle lands in one of these intervals, well, it's just the length of ij divided by the length of the interval itself. And then we just sum over all these contributions. And what we see is that the j cancel out, and so all scales contribute equally. And so what this tells us is that the total push that the right extremum gets after an arrival is given by, well, number of scales times the push that it gets from each scale. And the number of scales here comes from the minimum scale, which is size 1 over square root of n. And well, so this computation tells us that the total push is of order log n over n times L times the number of arrivals. And we can use this to get a differential equation for the length. If this is how the right extremum moves, then the total push that the length gets in n arrivals is just twice the push that each extremum gets. So the 4 became a 2 here. And this can be made into a differential equation for the length, which we solve to get square root of t log n. So this is where the square root of t log n comes from. And finally, to deduce geometrical information on the cluster, we want to show that the cluster has bounded height and that the diameter is concentrated around this again. So for bounded height, this is a standard argument. The height has to be bounded by 2 square root of t, because we know that if a point is in the cluster, then the half plane of the cluster is at least the imaginary part squared divided by 2. That's a standard estimate. And so if the height were to be larger than 2 square root of t, then you would be able to find a point in the cluster with height larger than 2 square root of t. And that would tell you that the half plane capacity is it's larger than 2t, which you know to be false. The cluster is rescaled to have half plane capacity 2t. So the height has to be bounded by this constant. We just care about the fact that it's a constant depending on t. We don't think that this to be the true behavior of the height. And we can use this to deduce that the diameter is diverging logarithmically. So you can argue by contradiction. Suppose that the diameter is smaller than 1 minus epsilon times square root of t log n. Then the cluster will be contained in a rectangle which has height of order 1, order bounded by 2 square root of t, and length, base length, bounded by 1 minus epsilon square root of t log n. So if I call r and minus r the base points of this rectangle, and then map out the rectangle via this map phi, which maps out the blue rectangle. So it's the unique map that maps the complement of the rectangle in the upper half plane to the upper half plane. then the boundary of this rectangle will get mapped to this blue interval, and by monotonicity, the cluster gets mapped to this red interval, which is contained in the blue interval. And well, because the height of the rectangle is of order 1, one can show that this red point, this R here gets only moved by a constant of order 1, constant depending on time. And so this tells us that R is bounded by, well, 1 minus epsilon divided by 2 times square root of t log n plus a constant. But R is smaller than square root of t log n. You add a constant of order 1, it stays smaller than square root of t log n. So that's a contradiction. In other words, the probability of seeing this picture is the probability that R is much smaller than what it should be. So this probability is very small. Okay, so this is the proof of the result with Nathaniel on explosive behavior. And I would like to tell you where one should go next with these models. So something I haven't commented on is the distortion intrinsic in the model. So remember, you have your cluster with k particles, map it out. This gives you a random interval. There you pick a uniform point, draw a slit of length 1 over square root of n, and then map it back on the actual cluster. So this slit is deformed by this map phi k, which grows back the previously arrived particles. And one could ask, how much does it get deformed? And so if particles are small, well, you can approximate the length of the particle in the actual cluster by, well, the distortion factor, which is the modulus of phi prime, the derivative of this map phi k, at the attachment point. So the length gets multiplied by this distortion factor, and the distortion factor is random in that it depends on the map phi k. In fact, it depends on the map phi k prime, which is worse than the map phi k. The behavior of phi prime is worse than the behavior of phi k on the cluster boundary. And so geometrically, because phi prime is inversely proportional to the harmonic measure on the cluster boundary, what this tells us is that if you attach to regions of the cluster which have high harmonic measure, then you will attach small particles in the actual cluster because this distortion factor will be small. Whereas if you attach in particles of the cluster where there is a low harmonic measure, so where you're unlikely to hit, then you will attach large particles because this distortion factor will be large. And this distortion is intrinsic to these models, but it's unphysical. You would like particles to have roughly the same size in the actual cluster if you want to mimic DLA, for example. And so an idea that goes back to Hastings and Levitov is to say, well, roughly then, rather than attaching particles of the same size, we attach particles of random size so to make sure that in the actual cluster, their size will be roughly constant. And so you want to compensate for the distortion factor, so you have to attach particles of length inversely proportional to the distortion factor, which will give you particles of roughly constant length in the actual cluster. And so mathematically, this is a big change in the definition of the model, because now the size of the k+1 particle here in the left picture depends on everything that happened so far in the model. It depends on the map phi k, which encodes the growth of the first k particles. And in fact, it depends on it via phi prime. But because you are touching according to harmonic measure on the cluster boundary particles of roughly the same size, this is a good candidate for a continuous version of constrained diffusion limited aggregation on the upper half plane. And Hastings and Levitov propose to modulate the compensation that we're introducing for the conformal distortion via an exponent alpha. So they say we could attach particles which size is inversely proportional to the distortion, to a power of the distortion factor, and that power will be denoted by alpha over 2. And so this will give us particles in the actual cluster with size given by the distortion factor to the power of 1 minus alpha over 2 divided by square root of n. This dividing by square root of n is due to the fact that we would like the capacity to be of order 1. And the reason why they introduce alpha over 2 is that they don't work with slit length, they work with capacities, and the capacities scale like the square of the length. So the half-plane capacity of the k+1 particle will be proportional to, well, a constant depending on n times the harmonic measure close to the attachment point to the power 2 minus alpha. And so this is a one parameter family of models that we would like to understand. And the question is there a phase transition? So we know that if we don't try to compensate for the distortion, which is the case we studied so far, there is explosive behavior. So the diameter of the clusters goes to infinity. But if you compensate for the distortion, say you take alpha equals 2, which corresponds to particles roughly of the same size in the actual cluster, do you really still have explosive behavior? We think that there should be a phase transition between explosive to non-explosive as alpha grows from 0 to higher values. And the question is, where is the phase transition? Is it at alpha equals 1 or a smaller or larger value? And I should mention that this kind of models are known to undergo a phase transition as alpha goes from 0 to higher values. And so for this, let me go back to the original version of Hastings Levitov aggregation models, which takes place on the complex plane outside the unit disk. So the definition is as before: you start from the unit disk, you want to aggregate particles outside the unit disk. And the way you aggregate particles is you apply conformal maps, you compose conformal maps, one for each particle arrival. And the conformal maps are random in that they depend on the random attachment points, like the random attachment locations that we had earlier. And they also depend on the particle sizes, which if we want to implement Hastings and Levitov ideas, we should take to be random according to the conformal distortion, according to the harmonic measure close to the attachment point. So this gives a one parameter family of models in which, well, the attachment locations are chosen to be uniform on the unit circle because we want to use harmonic measure. And the particle sizes here measured by capacity are inversely proportional to a power of the harmonic measure on the cluster boundary. And what Hastings and Levitov argued is that with these choices of parameter, the clusters should grow roughly like according to harmonic measure to the power alpha minus 1, which means for alpha equals 1, alpha is this exponent here, for alpha equals 1, we should see roughly uniform growth on the cluster boundary. And so that should be a candidate for the Eden model directly in the continuum. For alpha equals 2, we should see growth according to the harmonic measure. And so that's a good candidate for DLA. And in between, we should see growth according to a fractional power of the harmonic measure, power alpha minus 1. Whereas below 1, we should see growth according to a negative power of the harmonic measure. So what this suggests is that there should be a phase transition at alpha equals 1. If you grow according to a negative power of the harmonic measure, then you penalize the formation of arms and fjords. And so you expect nice clusters, roundly shaped clusters with microscopic fluctuations. Whereas above 1, you expect macroscopic fluctuations. So that's what they call turbulent behavior, since you're growing according to a positive power of the harmonic measure. And what we did with James Norris and Amanda Turner is we studied this family of models in the regime in which we expect to have scaling limits. And indeed, we proved that for all alpha in 0, 1, so in the whole regime in which we expect to have a deterministic scaling limit, the map phi that grows the cluster up to the NT particles normalized to have capacity 1 goes to the identity map as n goes to infinity, meaning that the clusters converge to disks as n goes to infinity. And I should mention that we study a regularized version of this model. We don't really evaluate the derivative of this map on the boundary of the cluster. We evaluate it slightly away from the boundary of the cluster. And this sigma here will go to 0 as n goes to infinity. Slowly enough, we have some assumptions on sigma. And in fact, it's important to tune the speed at which sigma goes to 0 appropriately, because if it goes to 0 too slowly, you just don't see anything. And if it goes to 0 too fast, then the behavior is too singular and the analysis becomes much, much harder. So we have a disk shape, and we can also prove that there is a fluctuation result that goes with it. So take this difference, this is going to 0 by the shape theorem, blow it up to see something non-trivial, and we show that this sequence of holomorphic functions converges to another holomorphic function outside the unit disk, which is conveniently described by the solution of this stochastic partial differential equation. And the thing I want to emphasize here is that the alpha, which is the exponent in the particle sizes, appears in the drift of this differential equation. So if you want to look at this limiting fluctuation field more closely, you could think of expressing it in Laurent series, since it's an analytic function. And what you get is that each Laurent coefficient behaves in the following way. If you ignore this 1 plus alpha t, then it will behave as an Austin-Uhlenbeck process, and the driving Brownian motions are independent. This 1 plus alpha t comes from the fact that the particle sizes decay in time. And so the fluctuations become smaller and smaller. And so there is a phase transition in the fluctuations since when alpha goes from 0 to 1, the drift term here becomes smaller and smaller, and it completely disappears at alpha equals 1, meaning that when you're subcritical, so below the phase transition point, fluctuations of higher Fourier modes contribute less, whereas at the critical point, all Fourier modes contribute equally to the fluctuation field. And let me close by saying that, in fact, we analyze a richer family of these kinds of model. You could try to compensate for the conformal distortion by tuning the particle sizes according to a power of the harmonic measure close to the landing point, but you could also try to compensate by tuning the angle distribution, so the attachment points distribution of a power of the harmonic measure on the boundary of the cluster. And you get a two-parameter family of models depending on which exponents you choose there. And here, this point is, well, the easy point in which both exponents are 0, so you're just composing IID maps. And that's the version that we studied with Nathanael on the upper half plane, so there's no feedback. Well, we have some feedback coming from the fact that the growth is constrained on the interval, but there is no feedback in the size of the particles. This is the region that we proved to have deterministic shape limit and Gaussian fluctuations with James and Amanda for Hastings Levitov models. In fact, we also proved that the same behavior holds for this entire infinite region. So you can move along this dotted line and you get similar behavior apart from time rescaling in the fluctuations. And so this in particular includes well, the best candidate that we have for the continuous version of the Eden model, in which alpha equals 2, so particles have roughly the same size in the actual cluster, and the growth is expected to be uniform on the cluster boundary. So what we did with Nathanael with the constrained Hastings Levitov model on the upper half plane is just the beginning of the story. we would like to add feedback in the particle shapes or attachment points, depending on which is more amenable to mathematical analysis, and see whether the explosive behavior is lost under the introduction of these exponents. So I'll stop here. Here are some references. The first one is the original paper by Hastings and Levitov, in which they define this one parameter family of models. The second is our explosive result with Nathaniel. Then I included the two papers with James and Amanda on Hastings-Levitov clusters, unconstrained Hastings-Levitov clusters outside the unit disk, in which we analyze this two parameter family of models. And I also wanted to mention that recently Noam Berger, Egetar Prokacha, and Amanda Turner published a paper on stationary Hastings-Levitov clusters on the upper half plane. So that's again Hastings-Levitov on the upper half plane, but the growth is not constrained to be, well, the cluster is not constrained to be a tree, meaning that particles are not forced to land on the previously arrived particles, but growth can happen everywhere on the upper half plane. So it's not even clear a priori that this model is well defined, and they analyze this model in this paper. Okay, thank you very much for your attention.
There's already one question by Genia.
Hi, I have a kind of a question about the same you've been trying to, this picture you're trying to give us here. In the middle, you says that the first model you introduced have some explosive behavior. Does that mean the model you introduced later, all those model which contain this conformer, I don't know, what do you call it? They are not explosive. I was trying to understand what you mean by explosive. Does that mean the image of the conformal mapping doesn't grow to the infinity or something?
So you mean what do I mean by explosive behavior in these models on the unit disk?
I think you mentioned you have explosive behavior in your first model, right? Yeah, right.
Yeah.
And you also mentioned
so by
you need this extra parameter alpha so that it doesn't explosive. But I was trying to understand what do you mean by this explosive? Like,
okay.
Yeah,
okay. Yeah. So by explosive behavior, we simply mean that the diameter of the cluster is diverging in n. So you rescale the cluster so that it should have size 1, where the size is measured by half plane capacity, whereas it turns out that the diameter of the cluster diverges as n goes to infinity. So that's what we call explosive behavior. And so the explosive behavior comes from the fact here all scales contribute equally, meaning that you get some push from particles landing close to the extrema, and you get, well, less push from particles landing far from the extrema. And you can quantify this by showing that all of these pushes give the same contribution. But now if you tune the size of the particles, so with this parameter alpha, well, that means that if you attach in regions in which you have, so think about alpha equals 2, okay? So then you are trying to compensate for the conformal distortion exactly, meaning that in the actual cluster, you expect particles of roughly the same size. But in our model, if you attach, say, close to the extrema, then you attach very large particles because, well, there is a distortion which is inversely proportional to harmonic measure. So the size of the particles that you attach close to the extrema, which have low harmonic measure, is large. But now for alpha equals 2, you will attach particles particles have to have roughly the same size in the actual cluster. So that means you attach particles of small capacity. So you get less push. And if you get less push from particles which land close to the right extremum, then, well, it might be that the push is still enough to give you explosion, but if alpha is large, then you might think that this push is not strong enough to give you explosion, and you might have that these right and left extrema move slowly, slower than what we observe when there is no feedback. And so that's why we think there is a phase transition, because for alpha large enough, you should not get enough push from particles landing close to the extrema. Does this answer the question?
Okay, thank you. I have another question actually. I have a question about your second theorem. You have this nice fluctuation on the capital phi,
Mm-hmm.
and you also have like the limiting distribution f, which satisfies this equation. I was wondering what is Cassi here? Does Cassi some noise term, or is this some
this one? Oh, this is just take Brownian motions in each Laurent coefficients.
Okay, so it's a Brownian motion.
Yeah.
Okay.
Just independent Brownian motion in each Laurent coefficient. So in particular, the Laurent coefficients behave independently.
Okay, thank you.
Asaf, you raised your hand before. Asaf, do you have a question?
So can I ask
Anybody
a
else?
question?
Yeah.
So I was under the impression that you said that you really need slits for the result, for the first result to work.
No, we think that the result is universal in a class of particles, as long as.
What is the problem in the proof? Because it seems you only need like
yeah, there's no
Taylor expansion of the function.
Exactly. No, there is really no problem in the proof. We haven't done it, but you really just need the Taylor expansion when you estimate the push coming from one particle that comes from the behavior of the conformal map, and if the particles are localized, they all behave the same.
Yeah. Okay.
There is a result in which, so most of our results, even for Hastings Levitov models, are universal in a large class of particle shape. And that we did in the papers with James and Amanda. But there is a version, there is one kind of result which is not universal in the particle shape, which is if you do Hastings Levitov, but you take this sigma here, this parameter here, you take it to be very small, and you also take this randomness to be in the angles rather than in the particle sizes. So you're doing alpha is equal to 0, eta is non-zero, and sigma is very, very small. So you're looking at the cluster very closely. You're evaluating the derivative very closely. And then it's a result of Alan Sola, Amanda Turner, and Fredrik Wiklund that you get a singular behavior. So if you start with a slit, then your large clusters will just converge to a larger slit. You will grow a single slit of the right capacity, and it will be randomly oriented just because the first slit is randomly oriented. And that depends on the slit because their sigma is small, so you're looking at the particle very closely, and you need the singularity of the derivative of the slit map. Whereas here we're looking at the particles from sufficiently far away, so we don't see the particle shape.
So can I ask, in your model with the Nathaniel, the